Hey guys, in electronics, if anything needs to work in synchronization, we need time so that the circuit in the system will have some reference with each other. And this time comes from an oscillator. I think you all must have watched the movie Lucy. Yeah, Scarlett Johansson gave the amazing performance in that movie. In that, she said,
Time gives legitimacy to its existence. Time is the only true unit of measure. It gives proof to the existence of matter. Without time, we don't exist.
and those words deeply penetrated my heart. Well, timing is everything. Today we'll see how does an electronic system stays in synchronization with each other. So, let's start. Oscillators generate the heartbeat of every microcontroller and produce clock signals that are essential for synchronizing internal operations. If you're using any circuit which uses frequency or synchronization or any type of activities in the circuit, you may need a brain, which is microcontroller. But you definitely need a heart, which is an oscillator. The electronic signal produced by an oscillator is basically a sine wave or a squared wave. An electronic oscillator converts the direct current into an alternating current signal. That sounds like a magic, right? These oscillators generate signals using the principle of oscillation. It all started with pendulum. In older times, the pendulum used to oscillate back and forth. Because of those oscillations, we used to count the seconds, then minute, and eventually hours. Well, this is the origin of oscillator. Basically, we need something which will mechanically oscillate continuously on a constant time period. This pendulum is a nice concept, but we can't put it in a small socket. So instead of that, we use resonators like crystal resonators or ceramic resonators. In this video, we'll see the crystal oscillators which are widely used in our electronic systems. As the name suggests, the crystal oscillator generates an accurate and stable frequency using crystals. These crystals are typically made up of quartz. You might have seen on your wristwatch or wall clock mentioning a word quartz on it. This crystal exhibit piezoelectric effect. That means when you provide any mechanical input to this material, it generates an electric signal because of its crystalline structure. We can also use these ceramic resonators, but they have higher frequency tolerance. That means the accuracy is lower with respect to temperature variation. But for microcontrollers in our electronic circuit, we need higher accuracy and stability. So we generally use the crystal oscillators. This crystal oscillator is equivalent to an LC oscillator circuit. The LC tank resonates at some natural frequency whenever we provide signal to this circuit. It provides oscillations because of the charging and discharging of these components. But after few oscillations, its amplitude decreases because of the internal losses of these components. So, to keep these oscillations constant, we have to continuously provide the signal to this oscillator circuit. For that, we can use an amplifier circuit. So the oscillator circuit is made up of crystal resonator, an amplifier circuit, and a feedback network. The crystal will resonate, which will create the electrical signal of the same frequency. The amplifier stage amplifies the weak signal from the crystal resonator and makes sure that the signal has sufficient strength to sustain the oscillations. And finally, the feedback loop provides the same signal with positive feedback to the same circuit. And that's how we get the constant oscillator signals. These signals can be of very high values up to hundreds of megahertz. There are different topologies where we can use crystal oscillator to provide oscillations such as Pierce, Colpitts, and clap oscillators. Out of those, the Pierce oscillator is mostly used in the digital circuits, which is made by using CMOS inverters and capacitors, which are called as load capacitors. Load capacitors help to stabilize and control the oscillation frequency of the crystal. Well, crystals are designed to operate at specific resonant frequencies. When we connect the load capacitors to the crystal, they form a parallel resonant circuit, which helps to get the desired resonant frequency. When we select a proper load capacitor, the crystal gets tuned into its specified resonant frequency, which produces accurate and stable oscillations. Crystals have internal parasitic capacitance due to their construction and mounting. These parasitic capacitances can impact crystals' oscillation frequency, but if we use load capacitors, they counterbalance the parasitic capacitance to give proper oscillations. Now we'll see some parameters of the crystal oscillators. First is the fundamental frequency. It is the resonant frequency at which the crystal vibrates. Next is the load capacitor, which we just saw. It is the capacitance required to achieve the resonance and stable oscillation. After that, the frequency tolerance. It is the permissible deviation from the specified frequency. Next is aging. It is the gradual change in the crystal's frequency over time. And then the temperature stability. It is the ability of the crystal to maintain its frequency across varying temperatures. Well, now we understood the basics about the crystal. But how do we use that in a circuit? These crystal output are generally in sine wave format. For example, look at this circuit. This is the 4 MHz crystal. It has the load capacitance which we talked about. Now I will turn on the circuit. If you look at the signal, it is 4 MHz crystal oscillator output. The waveform is in sinusoidal form. But there is a possibility that the circuit I'm using doesn't require this high frequency. I want a proper square wave which can be fed to some circuit like gate drivers. For that, I have to use some different type of circuitry. Let's say I have to use this crystal oscillator and generate multiple frequencies out of it. I'll take a circuit where I don't want to use any type of microcontroller for now. For example, I have this board. In this, we are using multiple frequencies such as 62.5 kHz, 31.3 kHz, 15.6 kHz, etc., which are required for this circuit, such as PWM, clock, or charge pump circuit, which we saw in the last video. We'll use the counter for this circuit. A counter counts the number of times a particular event has occurred. 1, 2, 3. No, not like that. There are two types of it. First is the synchronous counter and other is an asynchronous counter, which are also known as ripple counter. In asynchronous counter, each flip-flop represents a binary bit and can store either 0 or 1 state. The clock input is connected to the first flip-flop and the output of each flip-flop is the clock input for the next flip-flop. This cascading of flip-flops enables the counter to count in binary sequences. This is why this counter is also known as binary ripple counter. By combining an oscillator and a binary ripple counter, we can generate precise timing signals and divide frequencies. For this application, we're using 74HC 4060 IC. If you look closely in this circuit, it divides this 4 MHz clock and gives multiple frequencies such as 250 kHz, 125 kHz, etc. up to 7.8 kHz. And I can directly give these clock signals to this circuit. Coming back to the PCB, we saw this crystal circuit and this is the binary ripple counter circuit. You can see there are multiple test points on this circuit. If you measure these test points, it will give me square wave with some frequencies. I'm using test point 43. You can see at test point 43, The frequency is 250 kHz with the amplitude of 5 volts. I'll check the next test point, which is test point 44. At TP44, we are getting 125 kHz square. Just like this, we can generate a clock pulse using oscillator and a ripple counter. Well, these are some basic things regarding the crystal oscillators. I hope you picked up something useful from this journey. I'll back with some more mind-blowing content in the future. Till then, stay hungry, stay foolish.